Hello. That's 2018 clip 004. For you guys doing our class, we've been doing a project called magnesium burning with oxygens. It's oxidizing reactions. Um, in this particular clip, I try to do one more explanations, just going through, kind of revise well, what com what percentage compositions can be helped to find out a formula. In this prac, basically we know that we have magnesium metals, which is in solid form S, react with oxygen gas, which is gaseous form. We form some powder, which is magnesium oxide. For these, when we balance reactions, we know that there's two parts of magnesium is going to make two of MgO. Um, And the questions about this prac is why do we know that one, based on mathematically, why do we know this in particular is a the formula with MgO, not MgO2 or even Mg2O. So if we try to think about, there's a lot of different combinations you can make between magnesium and oxygens, but why do we have to be MgO, not something else? Then based on our prac, we have found one thing. We know that if we try to burn all the magnesium inside a crucible, so with the fire down there, so if we have a fire and all the magnesium metals inside should react with the oxygen coming in. So if you're talking about the mass of the oxygen coming in, those mass of the magnesium and the mass of oxygen coming in, if you add them together, all the mass would equals to the oxide that we have at the end of it. That one can't be something else because we cannot make any more or any less. Um, say, if this is 1 gram of magnesium, this one would be the x gram of oxygen would come in. The total mass of MgO has to be 1 plus x gram, right? 1 plus x. Can't be something else. It has to be like add together at the end of the day. So how can we use the compositions percentage to work it out? What do we expect to have? How much oxygen was going to go into the crucible and then try to react with the magnesium. So let's say it's 1 gram. We make it into 1 gram and then we try to apply into our real situations. Let's say if this is a magnesium oxide, then we've been learning about what would be the percentage ma mass in of the magnesium in MgO. We know that the magnesium is 24.3 from the periodic table out of the total mass of MgO, which is 23.3 plus 16. We find that the percentage of our magnesium would equals to 60.3%, like 24.3 divided by 40.3. Then, since we only have magnesium and oxygen in your compound, if 60.3% of magnesium is inside this magnesium oxide, if that one is 60.3%, the percentage of oxygen would be the rest of it, which is 100%, take away 60.3%, would end up with 39.7%. Okay? Assume all the magnesium, okay, all the magnesium is being burned and go into the magnesium oxide. So Mg, let's say we have 1 grams in there, and this 1 gram at the end of the day, when it reacts with oxygens, becoming MgO, these 1 grams go into the MgO completely. And part of the MgO here, and we know that according to the percentage, 60.3% is our Mg, and oxygen, which is 39.7%. Since 1 gram is what we have in there, and we can do a simple calculation saying that one weight 1 gram and that one weight x gram. If 60.3% equals to 1, what is the total mass of the MgO? The total mass of the MgO, we know that 60.3% of it would equals to the magnesium, 1 grams. Something 60.3% equals to 1. Then the mass of MgO can be calculated by 1 divided by 60.3%, which is 0.603. When you have 1 divided by 6.303, and we expect we have 1.66 gram come up at the end. Right? If you try to use the calculator, you can know that that would be 1.66. So Mg is 1 grams going into a reaction, and it's going to react with 0.66 gram of oxygen gas. And all together, when it forms, it becomes MgO. And all this MgO would weigh 1.66 gram in there. And the proportion between them is every 2 parts of a magnesium is going to make any 2 parts of magnesium going to mix up with 1 part of O2 and will form 2 bigger molecules, MgO. But overall, we have 1.66 gram in there. Now let's apply this into our situations. Our situation is a bit different. Instead of 1 gram, we have roughly 0.15 grams of Mg. So instead of 1 gram here, we know that MgO times up by 60.3%. That percentage never change because it's based on the formula. And 60.3% would equals to 0.15 gram. We only used 0.15, not 1. So change that into 0.15. Then the expected result that we find there would be 0.15 divided by 0.603, which is equals to 0.347. 0.347 gram is what we expected to form at the end. So since Mg is 0.15 and the oxygen gas that you expect to find that would be 0.343 minus 0.15, which is I can't do on top of my head, which is about how many gram? Let's do there. That one there, let's try to think that is 0.15, 0.347. 0.347 take away 0.15. 0.15 divided by 0.603. 0.248. Oh, something's wrong with my calculation. It's 0.249. So that one should be 0.249 instead. And 0.249 take away 0.15. Take away 0.15 would give us 0.098. 0.098, 0.098, 0.0988 grams of oxygen. integrate into it. Okay, um, so your prac, so something that you need to do is to show me that you know how to do these calculations. Okay, and based on your result, then you prove you need to show me one thing now, which is, just give me a second. That's a bit annoying. Just leave it there. So if we try to say that is your result, your Mg and O would be your result here. Then we find out one thing. Um, what would be, once you find out that, then we need to, uh, this is your expected result. And your expected result is used to compare with your experimental result. Your experimental result may not be 2.48, can be something else. So it may not be 2.4, maybe your experimental result for MgO at the end is equals to 0.233 gram. So this is from your experiment. Not not all experiment would be 100%. So if you get 95% is brilliant already. So how do we work it out, the percentage? Again, so we need to work out the percentage of 0.15 out of 0.233, which is your percentage, 0.15 out of 0.233. And we've got 64.3%. 64.4%. Instead of the 60.3%, you are slightly off from the experiment if your result is 0.233. Then what is your percentage of oxygen? Percentage of oxygen will be 0.0988 out of 0.233 minus 0.15. 0.233 minus 0.15 is equals to 0.083, 0.0988. What I'm doing? That one should be 0.083 is the oxygen, so and then over 0.233. That makes sense, huh? And it's 0.233. Sorry for those mix-up. And now we have basically the rest, 35.6%. Why do I need to do that? So once you find out this is your percentage, then this percentage can be used to go backwards. As the one that we try to do is doing the relative atomic mass and we'll try to find out the ratio between them. To find out the ratio between them, there's a shortcut to do, which is using this percentage divided by the relative atomic mass. You will be able to find out, by doing that, you'll be able to find out what would be the numbers that you expected to find in Mg in terms of just take away the mass situations. Try to do this. If we have the 64.4 over, because it's from magnesium, and magnesium has relative atomic mass of 23.3. So 64.4 divided by 24.3, we have roughly equals to 2.65. Then using the same thing, now we're using for the oxygen, and the oxygen percentage over the relative atomic mass would give us 35.6 over 16, which is 35.6 over 16. Then we have 2.23 as a proportions. So you're roughly saying that every 2.6 of the magnesium, you have 2.2 oxygens. So roughly you can say our result is not exactly what we expected. So what we do, the Mg ratio to oxygen is 2.65 to 2.23. By looking at that, that's not a whole number. We try to make that into a whole number, see whether we would be able to see a better relations. So let's say 2.23 divided by 2.23 is 1, and then 2.65 divided by 2.23 would give us 1.2, roughly 1.2. So when it's a 1.2, you times it by 5, so that is times by 5. You will probably, based on the result that we have here, we have 6 to 5 ratio, which is Mg, 6 of them would react with 5 parts of the oxygen. So this is our experimental result, and it's close enough to assume that is MgO. It's not exactly, but you'll find that that's the particular error. So instead of 1 to 1, you're 1 to 5. So this roughly how much percent is about 10% off of your result. So that's reasonable. And in your prac, that what you need to do is to show me those percentage and tell me, like, basically your results supposed to be 1-to-1 ratios MgO. But how come what would be the reason behind that you have Mg6O5 instead of MgO based on the result? Which what we have discussed in the class basically means that there's 2 reasons. The reason one is not complete reactions happening. There's no complete reactions. Still have some magnesiums not reacted. Some magnesium is not being reacted. It's still there as a magnesium. So that's not, you don't have enough oxygen goes into it. The other reasons, that is, magnesium metals would react with nitrogen gas. When it reacts with nitrogen gas, it forms Mg nitrate, which is Mg3 and 2. So we don't worry about like that too much as the compound's names, but this one basically is some impurity, which is not what we want. It's not what MgO that we want, and that one would create some kind of error that in our experiment. We call this error ERROR, and in your prac you should mention error, and then you have your conclusions after, right? Hopefully you have a bit better understanding about the prac, and I'll put up another videos later on, which is something that I like to explain with those prac and percentage compositions and find out the mole ratio between them. Okay.